Alright, so in this video I'm going to be explaining this important paper with the title Graph Recurrent Neural Networks with Attributed Random Walks. This KDD paper in 2019. So random walks are widely adopted in various network analysis, ranging from network embedding to label propagation. It could capture and convert geometric structures into structure sequences while alleviating the issues of sparsity and cursive dimensionality. Though random walks on plane networks have been intensively studied, nodes are often not pure vertices, but own different characteristics described by a rich set of data associated with them. These node attributes contain plentiful information that often complements the network and bring opportunities to the random walk-based analysis. However, it is unclear how random walks could be developed for attributed networks toward an effective joint information extraction. Node attributes make the node interactions more complicated and are heterogeneous with respect to topological structures. To bridge the gap, we explore to perform joint random walks on attributed networks and utilize them to boost the deep node representation learning. So it consists of two major components: collaborative walking mechanism and a tailored deep embedding architecture. We define a novel problem named random walk-based attributed network embedding and propose an effective framework. The other contribution of this paper is attributed random walks. We design a joint walk mechanism, this attri walk, which considers node attributes as a bipartite network and utilizes it to propel the random walks more diverse and mitigate the tendency of converging to nodes with high centralities. And based on this attribute walk, we advance graph convolutional networks to a more effective neural architecture named graph recurrent networks, in which node representations are allowed to interact within the same way as nodes interact with original attributed networks. You see, this defines a unified walking mechanism, this attributed walk. That we have this attributed network, and it enables joint random walks within network and node attributes, and a novel graph recurrent neural network to simulate attribute node interactions within the model. Here we sampled attribute node interactions. The attribute walk module is here that we will explain. So it would jump among all these n plus m nodes, the attributed walk, and assume that currently we have jumped to node I. To determine the next transition, we flip a biased coin. So we have this biased coin flip, and we flip it. We flip a biased coin that produces heads with probability I. Because we want to determine the next transition. If it yielded head, then we walk one step on G bar. If it turns tail, then we walk 2 steps. So if we either walk 1 step on G bar or we walk 2 steps on the A, because we have this attribute graph A as well here. We have this bipartite graph here, A as well. This bipartite graph, and for example, the edges for example, if node I contains attributes delta K, then we say delta K is in U. Because if you have bipartite graph, then the node I contains some attributes. So we either move one step on G or two steps on the bipartite graph. So if, for example, if it is head, then these are, for example, if it is tail, then we work two steps, as you see, two red walks on the bipartite graph. If it is tail, we walk on the graph just one step. So we either walk on this bipartite graph, or we either walk on that. It's very interesting to capture the attributes that and connect the attributes. And in the walking nodes, nodes in V could interact with each other not only based on the network Gbar, but also through node attribute categories. So this is the corresponding transition probability. And it has some nice properties in the theorems you will see. And this is the architecture of graph recurrent network. That it has a GRU, and then pooling, and then final embedding based on that, and then target such as label. We predict that. That is, everything is straightforward. And for loss, they use cross entropy error. But they just use a supervised setting, so they just use the cross entropy. And these are the data sets that they use. These are the baseline they use, like DeepWalk, like GCN, Graph Sage. And for different data sets like citation, Flickr, for example, this baseline DeepWalk, you can compare it with Graph RNA to see the node classification.